All right, so integration by parts. So integration by parts, the whole entire idea is I take a hard integral, whatever that means, and I change it into a easy integral, whatever that means. And what we've seen so far is, based upon the functions that are present within the integrand, I might want to do one thing or another. For instance, if I have the integration of x e to the 2x, I probably want to set u equal to the polynomial. Because by setting equal to the polynomial, it'll change a hard integral into an easy integral. But if I have something along the lines of, let's say if I have x, the natural log of x dx. If I set u equal to the polynomial, I'm going to have a big problem. Because if this is dv, I'm going to have to integrate the dv to get the v. But to integrate the dv is going to require another application of integration by parts. So if I see a transitional function, if I see a natural log, I want to bypass what we just said by setting u equal to the polynomial and consider what would happen if I set u equal to the natural log. And likewise, if I saw an arcsine or an arctangent, I would want to see what would happen if I set u equal to one of those two values. So based upon what's happened here with the integral, the integrand, one way or another. What if I had this one? The integration of e to the x cosine x. So we looked at what would happen if I had a polynomial times an exponential, and we also looked at what would happen if I had a polynomial times a trigonometric function. What if we got a little bit dangerous here and took an exponential times a trigonometric function? Cross our fingers and hope for the best. Well, again, I do identify a product being present. And whenever a product's being present that's prohibiting me from using a good old U substitution, a great technique to start exploring is what would happen if I just use integration of parts. So again, I got to make a choice. I got to make a choice here for you. And then once I make that choice for you, I'm locked in for everything else for my dv. All right, so let's say if I make a choice that u is going to be e to the x. Then dv is going to be everything. Du is going to correspond to e to the x dx. And to get the v, I integrate the dv. And when I integrate cosine, sine. So apply the formula precisely. U times v. Subtract it off, v times du. And take the integral of it. Okay, so now I got my other integral that I'm going to have to work with. So once again, I do see a product there. And whenever I see a product, integration by parts is a good procedure to explore. So let's do this. Last time we set u equal to e to the x. And again, I can do whatever I want. Suppose I set u equal to sine. There's no reason why I could not do this. Live on the edge. Explore. Dx. And v is going to correspond to e to the x. And again, I want to follow the formula right down to the last letter. So this piece is going to correspond to, we'll have u times v. We'll have the integration, we'll have e to the x cosine of x dx. And of course, I have this piece in front, e to the x sine of x. What would happen if I was to distribute now? I'll have e to the x sine of x minus a e to the x sine of x. And then I'm left with the integration of e to the x cosine of x. But that's what I got. Okay, so what happened was this. And once again, I made a mistake, right? It's the end of the world. Not really. Because through our mistakes, we learn something. And we're learning something right now. When I see these kind of situations, if I was going to set equal to e to the x, which is fine, if I was to reverse it at this stage, I unravel all the work that I just did. So I don't want to do that. So the mistake is teaching me, if I set equal to e to the x over here, keep it over here. And likewise, if I set u equal to the trigonometric function, at this stage, you would set u equal to the trigonometric function. Okay. All right, so let's go back. Instead of saying u is sine, let's say it's going to be e to the x, and dv is everything else. So if u equals e to the x, that's e to the x dx. And if I integrate the sine, what I'm going to generate is a negative cosine. What's the derivative for cosine again? Negative sine. So negative times negative gets me right back to where I left off. Okay, so I'm going to take all this. I'm just going to plug it all in. So we'll have e to the x sine of x minus, and I do see a subtraction, so maybe you want to encase this in a set of parentheses so I don't make a distribution error. I'll have u times v. Put the negative right there. Subtract it off, the integration. And because, again, that is negative, that's going to become positive. E to the x cosine of x. So I'll have e to the x sine of x plus e to the x cosine of x minus e to the x cosine of x. I give up. That's what I'm trying to solve. It came up again. I am so annoyed. You guys ever feel like that in math? Okay. Okay, so I'm kind of wondering why this is happening. That's just the scientist inside of me, breaking forth, like those Life's commercials from way back in. I like the frosted side, like the wheat side, the kidder side of me, I guess. Okay, so what am I solving for? I'm solving for this integral. And if I keep doing this process, would I expect anything different? If I do it again, it's probably going to take some terms off, subtract them off, and add them back. It's going to kind of go back and forth. So I can keep doing exactly what I'm doing, but if I expect a different result, I guess that's the definition for insanity. Okay. So what I want to do is take a step back and ask myself again, what am I really solving for? I'm solving for this, right? So what if piece right here and did a little pre-calculus with it? What if I called it I? Maybe I for integral. So if I have I, and let's just say I factor out the e to the x just to make it a little bit more presentable. you solve for I? You would take this, add it to both sides, then you would have two of them. So I really can use pre-calculus to help me in my calculus endeavors. Divide both sides by 2, and you got your answer. So the integration of e to the x cosine of x, I want to stop doing calculus when the integral pops up again. Give it some kind of variable name, I or maybe a or something, probably not x since that's already being used, but throw it to the other side and solve for it. And because we are talking about an indefinite integral, we'll tack on a plus c at the very, very end. Wow. Now, the first time I saw this, way on the other side of the building, I was like, whoa, that's like the coolest thing ever. Had like a mouth drop down and I couldn't believe it. You can use pre-calculus to do calculus. I was amazed. I can use what I learned from one class in another class. So in these kind of situations, the identity is going to spin back around again, and you're going to have to do something just like this. Now, here's a question I want you guys to explore later on today. Suppose if I have e to the ax, and let's say if I have sine bx dx. And also if I have e to the ax cosine bx dx. What I want you to do is see if you can develop your own formula here, going about this process. Okay, so see what you're going to get here for this one, and see what you're going to get here for this one. And if you give it to me Friday morning before the exam, sad to say again, that's all the time we have here for today. Time goes by fast when you're having fun, but don't worry, you can have some more fun later on here today with these trigonometric integrals. You guys have a great day. I will see you Friday morning.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.